My name is Andy Harris. I've taught computer programming for a lot of years. I've written some books about the topic, and I've had some YouTube successes in my conversations about how to become a programmer. But some interesting things happen. They're constantly, especially when I'm teaching, right? Um, when I'm done with a lecture, people will come follow me and they'll say, "Hey, I have a small question. I have a very tiny problem with my code." And that always cracks me up because I know what they really mean, right? If it was a tiny problem, they could have solved it. What they really mean is this is a problem that I've been stuck on for 6 hours, but I know you'll probably be able to solve it in a minute or two. And that's not always true. They overestimate me a bit, but it often is. Often it is true that the problem that they talk about is something I can solve, sometimes without even looking at the code. And that always astonishes them. But it shouldn't, because the thing is, first you have to be a programmer, and then you learn to be a good programmer. And a good programmer might be a person who can solve those problems, or more importantly, prevent them, to not have those problems happen in the first place. And how do you become a good programmer, not just a programmer? So this talk is for people who've already learned to program. If you haven't already learned some programming, this is going to be mystifying. I'm going to talk about terms you won't know. But I'm looking for people who maybe have already tried learning programming. You can write a few programs. And maybe you've taken a class. That's great. Maybe you've begun as a junior level dev, and that's all good stuff. But how do you become the good programmer? And most people assume the wrong thing. Most people assume that you're a good programmer because you've memorized all the syntax. Well, let me tell you something. If that's the case, then I'm a bad programmer. Because I regularly code in about a dozen languages between my various teaching and working. There's no way I've memorized all that syntax. That's ridiculous. Besides, I've got Google right next to me. Why would I memorize syntax? So, knowing all the codes, knowing all the commands, if that's not it, what is it? And I'll tell you what it is in this talk. What I believe it is to be a good programmer is standards, is discipline, is understanding some principles. So let me show you kind of what I'm thinking. So a good programmer is one who doesn't seem to make as many errors. A good programmer isn't thrown off by errors for long. If you've seen some of my programming videos when I live stream pretty much every code that I write, there's mistakes in it, and I leave them in there because I want you to see that when there's mistakes in my code, it doesn't throw me off for long, and that is mystifying, right? How do you get to that point? Experienced programmers have good coding habits. Now, sometimes these habits are called standards or rules or something, and that sounds horrible. That sounds like you're imposing something on me, and a boss or a teacher will do this. We'll provide some standards that you have to follow. But those are not bad. Those are not restrictive if they're good standards. The point is they prevent certain bugs from occurring. And so what I want to talk about today is the standards that I use not only for my classes and generally in my books and other writing, but also for myself. So when I'm writing my own code, I tend to follow all these rules. And well, I can write a lot of code and I can debug code well. So maybe it's opinion. This is all opinion, no doubt. Um, but you think about this: if a person has enough gray hair, check, and if a person's opinions or advice has proven time and time again to help people, maybe it can begin to move from the realm of opinion to wisdom. And that's up to you. I don't know, but that's what I'm gonna assert, that this is advice that I've given to lots of programmers, and it has helped them to become very good programmers. I want to also think of this analogy, right? You drive on a road and you have those guardrails, right? Well, that's rude. You crash into them, it'll hurt your car. And what's ruder is they keep you from driving off the road, right? If I'm on a curve, I'm like, I could just cut through that curve, right? Run over the fields, run over, oh, that's bad, right? Although the guardrail feels restrictive, the point of the guardrail is to keep us safe, is to keep us from going off road and flipping the car and setting it on fire and hitting pedestrians and that sort of stuff. And I would argue that coding standards, and all of them are up to you to decide whether you want to use them, but coding standards are guardrails that help keep you safe. And good programmers tend to have a set of guidelines. They might be mine, they might be different. But I'm just telling you what mine are, because after a lot of years of teaching programming, these standards have helped a lot of people. Okay, so we're going to begin with what I think is the most important thing, documentation. Or when I say documentation, I also mean a written algorithm. So documentation isn't just how do you use the program. That's fine, that's important, that needs to happen. But I'm talking about coding documentation, deciding what it is that you're going to do. My number one piece of advice is you must have documentation. In my class, if you come to me with a code and you don't have documentation, I will send you back. Show me what you're trying to do, then we can talk about how you do it. So in my classes or in my own internal stuff, I say to myself, look, the documentation could be internal, could be in part of the code. It might be in a separate file. It might be both. Depends on where you are in your life and what kind of a problem you're solving and who you're working with. But as a minimum, you should have documentation that describes what the program does. You should have at least a quick description of each function. And anytime you back up from the keyboard, say, whoa, that was a clever little line. Clever means in a week you won't understand it. So document that line, maybe even change it so that you'll understand it later. And then sometimes, depending on, again, your class situation or your job situation, you might be required to include documentation in a certain format. Like in some of my classes, I expect you to write your documentation in MD format, and there's specific things I look for. And I'll show you that. So here's what I require in my classes. And people are upset about it at first, but when they get in the habit, they like it. Because here's what I'm going to say. For every program or every function that's not obvious, you should have these 4 pieces in your documentation. I don't care exactly how you format it or anything, but I'm saying this. What's the goal of this thing? If you don't know what it's supposed to do, how do you know when you got there? I mean, and write it in English. Don't write it in math, or don't write it in programming. What is it that you're trying to accomplish? If you can't explain that clearly, you don't have any business writing that function. And then the next 2 are just a restatement of the goal with a little bit more specific. What am I expecting to bring in to this function or to this program? And that could be parameters that are coming in, that's user input that I'm grabbing, that may be networking stuff, whatever. What is coming in to my system? And what is going out? And are there particular rules? Are there particular expectations? Are there particular types of things that I'm expecting to come in and expecting to go out? Because really, the function is about how do I go from what comes in to what goes out. Now, some functions don't take input. Some functions don't produce output. That's fine. But in general, the point of a function is to either make something or to do something. And so we really want to know, what do we bring in? What do we send out? What do we do? And then the last part is yet again a repeat of the goals, but this time it's much more specific. And this is the steps in English. I like them in a list that explain how to solve the problem. Now, I'm not looking at code here, but I'm looking for such specific concepts that each line of the steps should be translatable to a line or 2 of code in whatever language. So I don't care what language we're talking about. I'm just saying, hey, you write down your steps so precisely that you can Google each line and have a good shot at getting that to the code. And that's separate from writing code. You don't begin by Googling to figure out what to do. No, decide what it is you're trying to do and then use Google to figure out how to do what you've decided. This is a profound change in the way that most beginners, in fact, a lot of experienced programmers work. But I'm telling you, you get into this habit and you'll be good. And I'll say this, in my classes, if you do this step well and you don't write a line of code, I'll still give you half credit. I don't have to do it very often, because if you do this part well, you typically write the rest of the code without trouble. It's true. Okay, so documentation goals. Again, it'll depend on context. You may have a boss or a teacher who tells you exactly what to do. You might put the documentation internally, especially as a beginner. I like it right there. But then as you get more intermediate, the documentation or the algorithms get a little more complex, and sometimes I'll have them in a separate file. Here's probably my most important, most profound, and perhaps most controversial statement. Documentation, by this I mean algorithm documentation, not the how you use it documentation. Those are different things. Algorithmic documentation should be written before you write code. In fact, it can be written before you've even chosen a programming language. I've done it. Right? You don't do code documentation after the code. You do documentation before the code, at least the algorithm piece, that goals, input, output, steps piece. And that's because of this. This is the most profound thing on that. The algorithm is not there to explain the code to programmers. The code is there to explain the algorithm to the computer. So you write the algorithm first in a human-like language, and then you translate that to code to explain to the idiot computer what it is you want it to do. Try it. It will change your life. 9 times out of 10, when somebody comes to me and says, I know what I'm trying to do, I just don't know how to do it, they are incorrect. 9 times out of 10, probably it's more than that. If I ask to see their algorithm, they don't have it. They don't really know exactly what it is they want to do, so they don't know how to look it up. So it turns out that they don't know what they want to do. And of course they don't know how to do it. You don't know how to do it if you don't know what it is. So this is probably the most powerful change in your thinking that you can do as a programmer, is begin by writing clear algorithms in English or whatever language is comfortable for you, if English is not your native language. And then take that step-by-step algorithm, translate that into code. Now, depending on the kind of projects, you may have to do other kinds of documentation like ER diagrams, UML diagrams, use case analysis, data flow. And as you get to those in your classes, great, do them. But the most important documentation, I think, is this algorithm step. And I would say the difference between a confident programmer and a hesitant programmer is algorithm development, is logical thinking, period. That's it. It's not about the syntax at all. Go ahead and look that up. I don't mind. But you can't look up algorithms very often. You pretty much have to be able to come up with those. All right, let's talk about some other rules or guidelines. One of my big things is concise coding. And here's what I mean. Sometimes I'll run across a student who writes a line like this, right? The X gets parsed, ran to A, process B. What language? Doesn't matter. I don't care. Here's the issue with this line. It's doing 1, 2, 3, maybe 4 things the way, depending on how you count it. And look at this. You just about can't write that line without counting the parentheses to make sure they all match up. And I would say this, whenever you have a line that's trying to do 12 different things, that's going to be the line that breaks. I mean, every time you add complexity to a line of code, you're making it more likely to break. And here's the thing. When it does break, just because you counted the parentheses wrong, or you just did too much at once and you forgot what you were doing halfway through the line, how are you going to fix it? Well, you're going to break it into several lines of code that each do 1 or 2 things that are more clear. And my argument is this: why not just start there? Why not just say, as soon as you write a line like this that's trying to do 12 things at once, just say, I'm not doing that. I'm going to solve 1 line at a time. I might have to create a couple of temporary variables. Oh, that's incredibly wasteful. No, it's not. No, it's not. Your computers today have ridiculous amounts of memory, and changing the number of lines in your source code has very little to do with the efficiency or the length of the compiled or interpreted code. You might have to just trust me on that, but the fact is the number of lines in your source code is irrelevant. What's much more important is that it's clear and easy to understand. So fewer lines does not mean the code is more efficient, and it doesn't mean the code is simpler to use. So I actually have no problem creating temporary variables, especially in the context of a function. They'll go away when the function goes out of scope, so no loss there. And I would rather my code be clear than short. So think about that. Think about that. Optimization. This is one of my favorite. If you take one of my classes and you raise your hand halfway through, professor, are you aware that that is a big O of n squared? I'm like, stop it. Stop it, stop it, stop it. Optimization sounds like a great idea, and it's one of the things we do talk about in computer science all the time. But it can wait. Many of the optimization ideas that we know about came about in the 50s when processor access was rare and valuable, memory was priceless, and programmers were cheap. Today, you can go to a conference and pick out a Mint and then scoop up a like a USB stick with memory on it. It's free. We have more processing horsepower in our phones, and in fact in our tires than some of NASA's earliest developers did. So it is still important at some point to optimize. I teach game programming. There's places there where optimization is critical. But the most inefficient part of modern coding isn't the processor bottlenecks or memory bottlenecks. It's programmer bottlenecks. So we're going to begin by making our code clear for the programmer. Begin by making your code easy to understand. It's wonderful to worry about time and space efficiency later, but it really is irrelevant if the code's not working yet, right? Don't tune up an engine that isn't running yet. Well, it sounds bad. Well, of course it does. It's not working. Let's get it working, and then we'll improve it. Here's one of my favorite quotes about this. Premature optimization is the root of all evil, which sounds funny until you understand the guy who said that. Donald Knuth is the guy who invented most of algorithm analysis. When you try to show off by talking about big O notation, Donald Knuth is the guy who invented most of that. Okay, and he's saying premature optimization is the root of all evil. So I feel pretty good in saying you can wait on optimizing until you get your code working. A lot of times beginners try to sort of show off on that sort of stuff. Other places they'll show off as doing all kinds of error checking before the code is even working. Yeah, error checking again is great. But if your code's not working, it's not time to improve it yet. It's time to get it working. So I'd rather get it working and then improve than get yourself kind of tied up into these secondary issues like error handling and optimization. Those can wait. I'm not saying they're not important, but I'm saying they can generally wait. And a lot of times optimization isn't necessary at all. Wait until you need it. That's why we have algorithm analysis, to find the places where optimization is necessary and do the hard work of optimization only in those critical sections. All right. Indentation. This is one of my favorites. Indentation, as far as I'm concerned, is not optional. I don't care what the compiler or interpreter says. Indentation is one of the biggest tools that a developer has to make sure that you are understanding what your code is doing and how your code is structured. So I'm going to say you always indent the content of every branch, every loop, every function, every class. And even if it's a one-liner and you don't have to, do it. Always indent. Always make sure that if you're in a language that has outdents, like close braces, that they match up with your indents. I'm not going to get into fights about whether the left brace belongs on the same line or the next line. Be consistent. But definitely you want to make sure that whenever you create a structure, the closing structure is lined up with it. Even HTML, CSS, doesn't really matter. That things line up so you can tell when things are ended. All closing braces look the same. So what I tend to do is I tend to label all my closing braces with a comment to say what it is I'm ending. And if, and for loop, and while loop, and function, and class def. And that should help me, that and the fact that they're lined up should help me make sure that I have closed everything that I have opened. All right. If you think you're done coding and you aren't all the way back at the left margin, well, you missed something. So you definitely use indentation to help you. A lot of times I'll have students come to me saying my code is broken, and I'll look at their code and the indentation is just atrocious. And I'll say, well, come back to me when you've indented properly. And the next email, usually they don't come back because they're embarrassed. The next email is, never mind. And it sounds just like that when I read the email. Never mind. Because the process of indenting properly helps you see where there are flaws in your logic, where you have forgotten to end some structure that you've begun. There's nothing wrong with that. But again, what are we talking about? We're talking about trying to prevent errors. So rather than having your compiler, and it will come back with bizarre errors if you miss things, right? A lot of times the error message is not, hey, you forgot to end something. It's that it sees something else it doesn't know. And so a lot of times those error messages are not helpful. The compiler doesn't know how to report that typically. So your indentation, your coding discipline is how you're going to prevent a lot of those problems. Most editors, even really streamlined ones, have some tool to allow you to match braces. So when you highlight one brace, it'll highlight the other one. Sometimes you'll see little lines in your editors. So if your editor has tools to help you ensure the blocks are lined up correctly, that's terrific. People have passionate fights about tabs or spaces. My opinion on this is use whatever you want, but don't change it. So within a file, within a project, if you're using tabs, use them everywhere. If you're using spaces, use them everywhere. The most, the language that gets us in the most trouble here is Python, because it can look just fine, but if you have tabs on one line and spaces on the next, Python will be confused and not know the indentation is correct. There's tricks. My personal preference is that I always have my tab key mapped to 2 spaces, or 4 spaces occasionally. And then I don't use tabs at all for anything. That way it's always consistent, even if I move to another editor or something. But this is one of those areas where your teacher, your boss may have very specific requirements. 2 or 4 spaces is pretty common. I wouldn't go much deeper than that. So if you're finding your indentation is taking you all the way across the page, right? So you're way over here now. Then maybe you should refactor your code. Maybe some of that stuff that should be a function. Or maybe you could think of using a data structure to simplify your coding. That's always worth thinking about. Okay, let's talk about variable names. This seems easy, right? Easy stuff. Variable names. Variable names should generally be full words or phrases. R is typically not a good variable name. George is not a good variable name. A variable should be about the thing, not about a particular one. Single letter variable names were required in a much earlier time in programming, and they are no longer necessary and generally shouldn't be used. There's a few exceptions. X and Y are okay when you're doing a math problem where you're talking about X and Y, or when you're doing maybe a graphic situation when you're talking about X and Y coordinates and Z and so on. That's fine. If that's what you mean, X and Y, they do have meaning. But I wouldn't use X and Y to mean something else because there's usually a more descriptive name. Card name or username or something. So don't use X and Y unless what you're talking about is X and Y. The other single letter variable name I see frequently is I, and that's fine in the context of a for loop when there's not a better name. So there's times that it doesn't really matter what you call it. So I is fine. That comes from Fortran, where integers had to begin with I, J, K, or L. Did you know that? Yeah. But it's fine. But if there's a better name, use it. Variable names should indicate what the variable does. Sometimes I see really cute variable names, foo and the thing and the other thing and Frank and so on. And that's just going to be cute for about a minute, and then it's going to be frustrating. Here's one I love: avoid abbreviations. People will push back on this. But I'm going to say every time you abbreviate, you forget the abbreviation and you get it wrong somewhere else. So the best way to get your abbreviations to always be consistent is to not use them. So a variable called username is way better than one called UN. Does that mean United Nations? Does that mean on something? Or uname? And I've done all those things. But if you want to prevent syntax errors from mistyping variables, then your best bet, especially if you've got a lot of variables, is to not indent, is to not abbreviate. I will combine them into a single word because parsers don't understand spaces. So it's always a single word, and we'll have some conversation about how exactly we capitalize those. Also, it's a good idea to use really specific name because keywords can get into trouble. Name is one of my favorites. Very, very many languages have the term name as a reserved keyword. It's part of the language. But it's also really common to want to have a variable called name. Some languages will allow this and some won't. Regardless, it's going to be confusing. So a lot of times I will tend to go with more specific variable names to avoid overstepping keywords. So username or last name and so on. So that's just a good idea. Now, does this slow you down? Yeah, and that's good. All right. So typing has never been the bottleneck of programming. So having to type a little bit more, it may slow you down a touch, but it won't slow you down nearly as much as having you name somewhere and you names somewhere else and trying to figure out why your program's not working. So I think it's worth it. And remember, when we compile or interpret the language, the variable name disappears anyway. It doesn't remain as a part of the actual code, especially in a compiled language. So having it longer doesn't really cost you anything. Okay, let's talk about capitalization. And again, these are places where the rules may vary by language. Python, for example, does not use my standards, and so I get in a little trouble with some Python purists. And that's okay. And a boss may also have different rules, but you should be consistent. So here's what I use because it works pretty well in all languages. Ordinary variables, including instances of classes, should always begin with a lowercase letter. And that's most of your variables. 90% of your variables are going to be this. When you are describing the name of a class, that might feel like a variable, but it is not. It's an entirely different thing. So class names I prefer to have capitalized, so I have some clue it's a class, not an instance. That's especially important in a language that has both. Like Java's famous for this: color gets new color. And that's horrifying because the first color is the class name, the second one is the instance. Yikes. So class name should begin with an uppercase letter. Class instances should begin with a lowercase letter because they're variables. My preference is generally camel casing. It's called camel casing because when you combine words to make a variable name, which I encourage, use capital letters to separate the words so you can tell it's username. If you smooch them all together without the capitalization, it gets harder to read. And some languages, Python, I'm talking to you, uses underscores for the same purpose, and that is perfectly fine as long as you're consistent about it. Oops, sorry, I didn't mean to do that yet. Constants, or some languages don't have constants, they have other things that act like it, should all be uppercase. So num values, and since I can't use camel case there, I will use underscores to separate. And that's really helpful because if you find yourself in code changing the value of a constant, you know you're doing something wrong. Okay, so let's talk a little bit about how variables named well can lead to self-documenting code. And by self-documenting code, I mean the code that you look at and you understand what it means. This does not mean that documentation wasn't required. You still had to write the algorithm to get here. The difference with self-documenting code is, and this is a good thing, by looking at the completed working code, you can tell what it's doing without having to go back to the documentation, and that's a good thing. But I don't believe that having self-documenting code is a replacement for creating a good algorithm. It is a sign that you have created a good algorithm and you have implemented it well. Because people will come back and say, well, I hear all you talk about algorithms, but I write self-documenting code, so they're not necessary. And I'm just like, what? And that's fine. If you're able to succeed, whatever you're doing, if it's working for you, fine. I'm really talking to those of you who are like, I sure wish I could get better at this. And I'm just telling you that these habits will help you. You know you've done a good job with your variable names and your function names and so on when there's just about no way to explain a line of code that's more clear than the code itself, right? If guess is equal to correct, right? I love that. So apparently the user guessed something and somehow I have a correct value and I'm just checking to see if the guess is equal to correct. That makes me so happy. As opposed to something if PWD is equal to PWDA, right? The password is, we have two passwords. One was the password that the user entered. I'll call that one password. And the other one is the right password. I guess I'll call that password A, or maybe I'll call one PWD and I'll call one password. You see what a mess you could get into? Yeah. Think about your variables so that your code is almost unmistakable. Then you've created good variable names. Small pet peeve, array names can be plural, scores, values, users, but individual variables, scalar variables, typically should not be plural, right? Because they're about a single thing. Variable scope. This doesn't matter until you have functions or classes, right? But data hiding. Local variables are a wonderful thing because you don't have to remember them forever. You only have to think about them in the context of a function. But every global variable is now something you have to think about all the time, and it's something that can go wrong at any time. So like most programming teachers, I generally am not a fan of global variables unless every single function uses it. There's still, we can use parameters and return values to pass data. Global variables are hardly ever really necessary. Global constants are fine because by definition, they're not changed. In an object-oriented programming setting, class level properties are not global. They are class level, and so they're fine too, but they should still be protected using getters and setters and data hiding and whatever mechanism you have in your language. Let's talk about file names. File names get people in a lot of problems. And I'll tell you, if you want to make your graders angry, there is no easier way than to mess up file names. Because in many systems, both school settings and work settings, there's some automated systems that are used to try and aggregate code and put it together and get it in the right place. And file names messed up is the easiest way to make sure nobody ever sees your code. So I don't care how brilliant it is. If it doesn't get to the right place, if the right program or person doesn't see it, it's not there. File names should be single words. When Apple started allowing spaces in file names and then Microsoft allowed the same thing, I just about wept real tears. Sure, for an ordinary user, that's fine. But we're going to tend to need to call command line compilers, and spaces cause all kinds of trouble. So don't put a space in a file name. Just don't. Make sure you're using standard conventions for your file names. If it's a C file, make it .c. C++, make it .cpp or .h. Whatever makes sense for your language. It isn't always required to do that, but it's still sensible, because when we look at your files, we need to know what's what, especially in a complex program that may involve multiple languages. Seems like a silly thing to talk about, but I've had people turn in their programs in .txt files and so on, and ooh, okay. Likewise, if your program creates files, the extensions should be standard when there's a good reason. Of course, you can make up your own standard. There's nothing wrong with that. But there's a few standards you should use. If you intend for this to be human readable text that they could pull up in Notepad or something, then it should be a .txt file. If it's comma separated values, or it's cousins like tab separated or whatever, .csv is appropriate. The nice thing about a .csv file is many operating systems will recognize that can be opened by a spreadsheet. And so that's nice to put out data in a form that could be easily read by a spreadsheet. If it's a binary file, I don't know, object serialization or something you created that doesn't have a more specific meaning, then I would use .dat. The thing about .dat is that signals to the user, you shouldn't open this in a text editor, because that could break it. So sometimes in an automated aggregation system, you might be given specific file names to use. If you don't use those names, if you don't use the directory structure and so on, then a lot of times these automated systems are not going to find your code, and your work will be considered a failure no matter how good it is. So spend some time thinking about file names and making sure you get that right, because I've seen a lot of people do great work that doesn't get noticed because they mess up this basic thing. Okay, let's talk about branching. So branching is if, else, if, switch, and so on. Many languages allow you to do a single line if statement that doesn't require braces. What happens is when a programmer does that, they feel very clever, and that's fine. But something happens, they realize, oh, I needed to do more in there. And it is pulling teeth to get them to switch it from a single line if to a multi-line if. The other thing that happens in this case is it's not always obvious, just glancing at the code, that there was a branch there at all. So since indentation is such a huge visual clue into the structure and purpose of your code, I would say I never use single line if statements. Even if it's a single line of code, I'm going to go ahead and put, if it's a C-like language, the squiggle braces, beginning and end, indent. Put that one line of code. Again, length of code in the editor has nothing to do really with the length of the compiled or interpreted code. It's the complexity that matters, not necessarily the length in your editor. So since those things will compile the same way, make it more clear. A number of languages have these clever ternary operations. If A is true, do B, else do C. That is clever and fun and occasionally makes you feel proud of yourself, but it has the same problem. People, first of all, it's not always immediately recognizable as a condition. And secondly, once you've built that, you never want to change it into something that takes multiple lines, even if that's the best thing to do. And that's just human nature. So I don't use ternary operators. I know how to use them, but I don't hardly ever, because if, else, and else if structures make a lot of sense. This one's controversial, and I'll explain it more as we get to loops. I love Boolean operators, and or not. I'm going to say if you're a beginner, you should be very, very careful about using Boolean operators in if statements or in while loops especially. And my personal rule for my students is, if you can explain De Morgan's law, which is an important rule of Boolean algebra, then you know enough about how Boolean algebra works that you probably won't get yourself in too much trouble. But if you're like, De Morgan's law, is that like Captain De Morgan? No, it's a different thing. Then there's alternatives. So I would say for a beginner, you can always use if and else if to get the same behavior as or. You can use nested ifs to get the same behavior as and. And so if you find that you have a complicated if statement or loop that's not working correctly, the vast majority of the time, if you break it out of if you break it up into smaller non-compound conditions, you're gonna get what you want. There's other advantages too, because I can do the else clause of each. Switch statements and select statements and the like. These are notorious for being non-standard, especially the one in C++ and Java. They require the use of the break statement, which always felt broken to me. They have this weird step-through behavior, which is hard for beginners to understand. Java, until very recently, only allowed you to switch on primitive data types, so you couldn't switch on a string. Python didn't even have switches. And the thing is, wherever you were going to use a switch, there are other things that could work. You could use an if-else if it's not too many elements. But a lot of times, when I was tempted to use a switch, I can use a function that takes in a parameter. It does the same thing. Or I can use an array if it's switching on an integer value, or a dictionary if it's switching on a string or some other kind of value. So switches aren't really necessary, and they sometimes get people into a lot of trouble, and they usually have a non-standard syntax. So I'm not a huge fan of them for beginners because they cause more grief than they're worth, and you can always do something else. If you are doing an else if, a clause with a bunch of else ifs or a switch, make sure that you have some sort of a default clause, an else, or a default or whatever, that actually triggers if none of the other events do. And sometimes you're like, okay, if the die is 1, do this thing. If the die is 2, and then I go to 6. Well, it can't be anything but 1 to 6, so why should I put an else clause? Well, if you've programmed more than 5 minutes, you know that things that should never happen all the time. And so I'm still going to put an else clause in there. If nothing else, it'll send an error message. Yo, the universe just broke. We rolled 7 on a die. Because you want to know that so you can figure out what's wrong with your code. Okay. Just good advice. Once you get past the very basics of programming, learn how aggregate data types work in your language. Lists, tuples, arrays, dictionaries. They may be called different things in different arrays, but these in different languages, but these things exist in every language, and they can be incredibly helpful. And a lot of times, using one of these tools could simplify your work quite a bit. Now, note if you're doing a beginning class, sometimes your teacher won't let you do this. For example, when we're first building linked lists in one of my classes, I don't want you to use the one built into the language because I want you to have the experience of building your own. So sometimes in a class setting, you'll have some artificial restrictions. Don't use this yet. I want you to understand a pure array before you use an array list. But once you're doing your own programming, knowing the distinction is really, really helpful. Equality operators. Be super, super careful about comparisons. Let's say I have 2 string variables, A and B, and they both contain the value foo. So A double equal B. Is that true or false? Well, same exact command, different behavior in different languages. C++ would say in that case that A contains the value foo, B contains the value foo, they are equal. Java would say A is a reference to an object containing the value foo, B is a reference to a different object also containing the value foo, they are not equal. Which one's correct? Yes, they're both correct. But you have to understand that equality is one of those things when you move into a new language, you always want to think about how do the equality operators work? And how do I make sure that I'm getting the kind of equality I'm looking for? JavaScript. Oh my goodness, JavaScript. Okay. Picking a loop type. So let's move to loops. So there's two main flavors of loops and a few variations, but every language I know has at least some form of a for loop and some form of a while loop. Loops, of course, are for repetition. But sometimes people really struggle on which one to use where, and I see people use the wrong kind of loop in the wrong situation. Here's how I like to think about it. For loops are deterministic, and what that means is as I'm writing the code, as I'm putting together the algorithm, I know exactly how many times something will happen. Now, that might be in a variable, but I know it. I know how many times something will happen. Most often, I want something to happen 52 times. Pick a card. Or I want something to happen for every element of a list or something. And so that's when you use a for loop. For loops are almost always about counting of some sort. And it's meant to be deterministic. Now, could we fake it and make a for loop not act that way? Sure we could. Terrible idea, because you're going to confuse yourself. But a for loop is useful for this deterministic situation. I know how many times it's going to happen. A for loop is ideal for iterating through a listable data structure. And in fact, languages now often have special variants like the for each loop or an iterator or something, which simplify that even more, but it's still really a for loop. It's about deterministic behavior. So what about non-deterministic behavior? Well, that's what while loops are for. So you'll typically want to use a while loop when the end of the loop is something you can't predict as easily. So it's going to be based on some event. The user clicks on a button, or the user finally gets the password correct, or too many turns have happened, or whatever. So we don't always know exactly what the end is going to be. And of the two, for loops tend to cause users or programmers far fewer problems than while loops. And there's a number of reasons for this. But for loops, by their deterministic nature, are more predictable and easier to write. The other thing about for loops is the things you need to know about a loop are built into the syntax of the for loop. Where in the while loop, you have to do the same things, but you have to understand, you have to write code elsewhere to make it work. What? Okay. Every loop has what we call a sentry variable. So a variable whose job it is to control access to that loop. For loops, as we've mentioned, we use I as the for loop sentry. If the name doesn't really matter, if it's just, hey, I'm doing something 12 times, I is fine. If we're going through a deck of cards, I would use card number, because now I know what that stands for. It stands for which card number am I thinking about? You seeing how I'm thinking? For double nested loops, it's traditional to use J. For triple nested, it's traditional to use K. Again, this is if we're not going to do anything else with that variable. If it's really just for counting, then that's fine. Most for loops in most languages have ways to count backwards, skip count. Python's for loop is extremely interesting. It's actually an iterator. So you want to have a conversation about that, we can talk about it, but it's not important. So with for loops, you can count backwards, you can count by 5s, you can count by -3s. You can easily make it not work if you're not careful about setting it up. It is possible to make a for loop act like a while loop. Please don't. Because why? Why make your life crazy when you don't have to? So while loop drives beginners crazy in a couple of ways. One, as I mentioned, is that you have the same issues in a while loop that you have in a for loop. And that is, I've always said, in any kind of loop, there's a sentry variable and 3 things you need to keep track of. How does it start? How does it end? How does it change? Okay. And in a for loop, those 3 things are usually built into the structure of the for loop. In a while loop, you have to write different code to do the different things. And there's another problem with that. The condition of a while loop indicates the condition that causes you to stay in the loop. Normally, in an algorithm, it's easier to think about when you will leave the loop. which is the negation. It is the opposite. And so often you have to think of the opposite of what you're trying to say. And that can sometimes be quite complex and hard to work with. And I've seen lots and lots of beginners run into problems with that. The other thing that they forget is they need to initialize the variable before the loop begins, and they need to change the variable inside the loop to guarantee that that condition can be triggered and they can get out. So it's bad enough with a really, really simple condition, right? If I want the loop to continue, so I'm going to write a loop, right? Are we there yet? So it's going to keep asking, are we there yet? And if the user says no, we should keep going, right? Well, it would be better to define it as the user does not say yes. So you see how while loops, usually the condition is negated. And this is bad enough in a traditional situation, but when you start to have compound conditions, A or B, what's the negative of A or B? That's De Morgan's law. That's why you should know it before you use it. Okay, so if you don't know what I'm talking about, fine. Just jump ahead to the next couple slides. But what I'm saying is people mess up while loops all the time because the logic is hard. Here's another thing I see people do all the time. If my var equals A or B, and in English that makes perfect sense. We're basically using the distributive law, right? If my var is equal to A or my var is equal to B. But that is not how it works in most languages. What this is going to do is it's going to say if the my var equals A, it'll calculate that. And then the or clause will also calculate separately, is B a thing? Has nothing to do with my var. Is B a thing? Does it exist? And if B is a thing, then the whole thing will be true. And because this is an or clause, it has no difference. It makes no difference whether my var was A or not. B is always a thing, and that entire condition will always be true. And so if this is in a loop, the loop is endless. It'll never stop. This is the sort of thing I see people get into trouble with all the time. And they're assuming it's a syntax error. It is not. It's a logic error. They're much harder to find. So you want to trap for this. And again, I would say the easiest way to trap for this is to say compound conditions, maybe not today, Zerd. Maybe we don't need compound conditions in loops. And I'm going to argue that most of the time you do not. So here's my solution to this. I've taught this to lots of people. And I'm telling you, if you're ever having loops not act properly, try this instead. So I argue that most of my loops have a Boolean variable as a sentry, usually something like keep going. And I initialize it to true because I want to keep going. All the keep going variable does is tell me whether I want to keep going or not. And when I don't want to keep going, I'll set it to false. When I do want to keep going, I set it to true. So we initialize it to true outside the loop. And inside the loop, if I have 10 different things that make me want to get out of the loop, fine. Put them in if statements. It's a really complicated combination of ands and ors. We've already said you can use parallel ifs and nested ifs to get that behavior and make it super clear. And in your basic conditions inside the loop, that's where you change the value of keep going. And the next time you get to the top of the loop, keep going will be false and you'll get out. This avoids all those issues with De Morgan's law. It avoids all the things that can go wrong with and or. Now, a lot of companies won't have this rule, but I'm telling you, if your loops aren't working and you have compound conditions, kill it with fire. Replace it with a keep going loop and see if that doesn't solve it. And very often it does. So what's the next thing? Just don't write those. I'm actually quite good at De Morgan's law. I've taught classes about it. I've written about it. I still use the keep going loop as my primary while loop most of the time because I'm good at De Morgan's law and I still don't like getting confused. Yeah. That's my favorite slide title of the entire talk. I'm just saying. Never been a fan of the break statement. Break statement is usually a sign that you're a lazy coder. It's mostly used in poorly designed structures. I despise its use in the switch statement in C. It should have been designed a better way, and it could have been. But it isn't. And I could be wrong on that. You could write me angry emails, AJ Harris. My least favorite part is these endless loops, while true. I see people recommending these all the time. And that is unfortunate because while true is a lie, you almost never really want a loop to truly be endless. What you're saying when you say while true is, I'm going to act like it's endless and later on I'm going to break out of it. Well, that's rude. It's not endless. Something will cause it to end, unless you're writing, say, a web server or a daemon or something. Those are the cases where I could think you might want to have code that feels like it goes forever. But that's rude. How could you resolve that without having break statements? While keep going. Same thing. So rather than while true, set keep going to true. And then when you want the thing to end, set keep going to false. Yeah. Especially I don't like loops that have multiple break statements because that can be very confusing to follow the logic of later. Typically, in a structure, I like to see one way in, one way out. That's going to be much easier to follow, especially if I have to do things like algorithm analysis. Functions. Let's talk about functions. A function's job is to simplify your life, right? How do you solve a really, really hard problem? Well, here's what you do. You take a sledgehammer and you smash it into a bunch of smaller problems. And you look at each of those problems and you see this one's still too big. Smash it again until your problems get bite-sized, like fun size, right? When your problems are bite-sized, and I would argue about the size that fits on one screen of your editor, maybe has no more than 7 to 10 variables in it. When your problem is that small, now you can start to write an algorithm that can get to it. A lot of times people look at a problem and it's so complex, they're like, I can't possibly break this down. Right, break it into functions, break those functions into functions, and eventually get down to the point where each function is solving one very specific thing. If your function does more than one thing, it's probably two functions. Right? And there's no overhead. It doesn't cost you more for it to be in more functions in most cases. Anytime you've got a repeated behavior, a complex behavior that could be named, good candidate for a function. Functions should be small enough that you can handle it in your head all at once, that you can understand the entire problem domain at one time. Think about this. If your phone were to ring in the middle of coding and then you have to answer the phone and stop thinking about your program, how long will it take you to get back up to speed in solving the problem that you're in? If you're working in a program that has a function with 500 lines in it, you're not going to get back in that space. If you can see the entire function at once in front of you and it only has a small number of variables, it's a much faster and easier way to get your head back into the space of solving that problem. So I would say more smaller functions is almost always a good idea. In object-oriented, functions relate to methods, but it's really the same advice. A function is about the space you can understand. That's the way to think of it. And if you can't understand the space, if it's too complex of a problem, break it down. Okay, while we're on functions, return statements are sometimes used like break statements. So a return statement has two purposes. The most important purpose is that it's a place to provide a return value for a function that produces output. And so that's wonderful. A side effect of that is that when it returns a value, it automatically ends the function. So some programmers will also use a return as sort of a glorified break statement to jump out of a function before it normally would. And while that's legal, like the break statement, I think it can lead to a lot of confusion. So my preference is if your function doesn't return a value, you don't even need a return statement. At the end, it'll be done. If your function does return a value, I prefer the return be the last line of a function. If there's code after the return, the implication is that this function isn't always the same, and that's going to be confusing. Now, you could do this, right? I might return different things, but have a variable, change the value of the variable, and at the end of the function, return that variable. Most times when people are tempted to use multiple return statements, they could just do one at the end and change a variable. Adding a variable is not a problem. That does not cause your program to be less efficient in any meaningful way. So making variables and clarifying your meaning is always, not always, but way most of the time worth it. The one place where you may want to think this through a little more would be in recursion. But recursion is not something I recommend for beginners to do until you're very comfortable with more traditional coding. Which takes me to my next point. There's really cool things you can do with functions. You can do inner functions, anonymous functions, lambdas, recursion. These are amazing techniques, and used in the right place, they can save you tremendous amount of work. But I see people use them kind of in the same way that we talk about optimization, way too early in order to show off. And usually when you show off, you end up, setting yourself on fire. So I would say don't use inner functions, lambdas, recursion, similar kinds of things unless you know that you need them. If it'll improve your code, great. Recursion, for example, is by far the best way to handle any kind of a tree traversal problem. But I don't usually give beginners tree traversal problems because beginners often aren't ready for recursion until you're really good at traditional functions. So this is just good old general rule. Don't get fancy unless there's a good reason. You will not impress anybody by doing something fancy that breaks. I've seen people in their freshman class try to do, a neural network over a wide area network and, distributed computing with, all this crazy minimax algorithms to solve tic-tac-toe. And if it's working, fine. But usually it doesn't. Usually there's disasters and somebody's computer is on fire somewhere. And I'm not impressed by trying to go huge and failing. I'm much more impressed by going small and building and getting something working and then moving better and better and better. When functions get too complicated, a lot of times you can change your code to data. And this is the purpose of a class. You'll eventually take data structures and algorithms. And then what you'll learn is that a lot of times we can improve an algorithm by converting it really to a special form of data. So thinking about things in terms of lists and tuples and arrays and dictionaries and linked lists and trees and so on can be very, very powerful and can take a function that's super, super complicated and actually make it quite easy. But again, that's not stuff that beginners need to typically do. It's usually taught in a second or third class for good reason. You need to make sure you understand the fundamentals before we start throwing crazy stuff at you. Classes. It's even debatable whether classes needs to be in an early programming class, but in some languages, Java, I'm talking to you, we don't have a choice. And so object-oriented programming, you can spend an entire course learning about that, but here's just my basic things about object-oriented programming. An object should have a meaningful class name. If you have an object, you have to have a constructor or initializer or whatever it is in your language. The constructor should initialize all of the properties of the class. If you can, you should make your properties private or protected. If you possibly can. There are a few languages that make this tricky. JavaScript. You generally don't want the user to be able to directly change your properties. If you don't know what I'm talking about, just skip over this part. So you want to use getters and setters, access modifiers to allow access so you can protect your data. If your language has a property mechanism that makes it feel like you have a property, class.name, but it's actually quietly calling the access modifiers, great, use it. It's wonderful. If you don't have it, fine. Getters and setters are fine. things like multiple inheritance and so on, they're kind of like recursion and lambdas and so on. This is a great idea that sometimes is really helpful, and it can also cause you ridiculous amounts of grief. So generally, I would stay away from it. And again, this is a more advanced topic. I would typically use other ideas, abstraction, aggregation, there's some well-known ways of getting the same behavior. If you don't know what I'm talking about, again, that's fine. Adding unit tests to classes. I already said this about functions. Whenever you create a new thing, you want to try and test it in isolation before you put it together with other things. Does that make sense? So you always want to test it in isolation and make sure that it works before you use it somewhere else. Now, you're not done at that point. You also have to do what's called integration testing. So as you're putting things together, you make sure they work well together. But a lot of times, the testing strategy that beginners use is none whatsoever. It either works or it doesn't. So I prefer, whenever I create a new thing, to first just test it and make sure it acts correctly in most situations before I start trusting that thing and using it somewhere else. Let's talk about debugging. Debugging is one of those things everybody says they should do and they don't. Maybe if we're lucky, we'll see people put print statements in their code and like masterclass. That's okay. These are called diagnostic print statements. That's okay. It's not an ideal situation, but it's fast. It works in every language or most. There's some game engines that I have trouble with that working in. But yeah, that's okay, but it's not ideal. Every language comes with debuggers. Debuggers often come with an IDE, but I'll talk about the alternative in a moment. Here's the thing. If your code has diagnostic print statements in it, that should not be part of the final code you turn in. I'm okay with it being there and commented out. That's okay, but it should not be part of final code. That's unprofessional. And honestly, what it says is you either didn't know how or you were too lazy to use a debugger. Learning a debugger is an absolutely critical part of programming. Now, sometimes debuggers are dependent on your IDE and so on, and that's okay. It takes some time to learn it. Spend that time. Don't learn the debugger when your project is due in 5 minutes. Learn the debugger before that time. Learn how to use a debugger on code that works before you're in a crisis. Most people don't learn debuggers because they wait until they need them, and then they're in a hurry and they're panicked. I would say this also. Every language I know of, in addition to having pretty debuggers that come with IDEs, has some sort of a command line debugger. If you learn one debugger, it would be GDB, the debugger that comes with C. And the reason is, while it's ugly and it's unglamorous, every language I can think of, at least most that I can think of, have some version of that. So it's always available to you. There's always some kind of a command line debugger available. It may not be pretty, it may not be glamorous, but I would say learn how to use at least one command line debugger so that when you find yourself in a situation where you don't have your pretty IDE and your code's not working correctly, you know how to check it. Debuggers are not there for syntax errors, which is fine because syntax errors are easy. Debuggers are there for logic errors, when your code is running but not doing what you want. No syntax error clause will help you there. You've got to look at your code. You've got to look at those key variables. You've got to make sure that they say what you think they say. When? How do you know that? Because you have your algorithm written down. See, it goes back to that. You know what it's supposed to do. Now you can compare what it's supposed to do to what it's doing. If you didn't write your algorithm, well, I would say I'm sorry about your luck, but I'm not. You've earned that luck. Some cases you'll need to know more sophisticated stuff, Valgrind and so on. I'm not going to worry about that for a beginner. A couple more sort of ancillary topics that are worth learning. Depending on your language, you might use something like Make or Gradle or something. These build tools that allow you to put together more complex projects and make sure that you get your dependencies right and so on. Make is the classic. It's the one I typically use for my classes. The most common mistake I see with this is people wait until they've written everything to write their make file, and that means they haven't been doing incremental testing. So you don't really know what's going to happen until you've written all 7 modules, and then you try to compile them and it doesn't work, and you don't know if it's a problem with your makefile or if it's a problem with your code or whatever, and you have this dreaded 5,698 errors, and it's due in an hour. Yeah. You shouldn't be waiting that long. You should be building your makefile as you go. You should be adding to it as you add new components. And you should design it so that if you have it at all, it has a run target, like make run, so you can easily run your code and just keep changing it. Again, if you're not using make yet, if your teacher's not asking you to, fine. If you're in a commercial setting, you may be using something else. CMake is a popular automated version of this. And that's fine. But you need to be thinking about your build process as you're going. Now, for a beginner class, we often don't worry about this because you're working about single file projects and you're often working in an interpreted language like JavaScript or Python, which don't really require that. Version control. I can tell you this, I've helped several of my students go interview with former students at big companies. And usually the first thing that people ask is not about what languages you know or about, what's the big O of a quicksort and that sort of stuff. No, a lot of times the first question is, tell me what you think about version control. Because this is really about your software engineering practices and your discipline as a coder. So wherever you are in your programming life, I would highly recommend you learn some kind of a version control. Git is the standard right now, and it's pretty great. So it's well worth learning. I explain it to people like this. If you're playing an adventure game and you see a bunch of health packs and a big door, what do you know, right? There's a monster behind the door. So before you go through that door, you pick up all the health packs and then you save. Because the first time you go through the door, you're going to get walloped by that monster and you want to go back to that save point. Well, that's what Git is in coding, is it allows you to create save points. And if you think of it that way, why wouldn't you want this, right? So every time you get up from your keyboard or every time you have your program at a state where it runs, maybe it doesn't run right, but it runs, make a commit. If you know how, I would say at particular milestones, you should also make a new branch and merge the branches. This is a skill you'll need to learn. I teach it in my CS2 class. But make sure that you have at least multiple commits and that you know how to switch between them so that if you have to go back to a save point, you can. I see a lot of people waiting until the project is entirely done to do the commit, and then you've missed the whole point. One other thing I would say, especially in current versions of Git, is try not to build a repo inside a repo. That always causes troubles. So each project should be an individual repo. Depending on the build system that your company or your school uses, you may have to have a very specific name on the repo because we often use automated tools to go extract data out of the repos. Okay. So that's it. And it seems like a lot of rules. Like it's like, seriously, I have to remember all this? No. What I'm saying is all of these ideas are ways for you to make sure that you avoid certain mistakes that are common and that when you are in trouble, you can get out. Do you have to do them all? Well, if you're in one of my classes, yeah. But if you're just learning, no, decide what you want to do. But I will tell you that the process of developing your own programming style is really about developing these internal rules. And when you get to a point where you've decided, okay, I'm going to use keep going, that's a really good idea. And I'm going to use version control, and I'm going to always test my functions in classes before I use them. And I'm going to use these naming standards. None of these rules are unreasonable. And together, they can help you with practice and experience be the kind of programmer who's better at solving problems. And you'll be surprised at some point, you'll be the one that people are going to saying, I have a little tiny problem with my code. And you'll be able to fix it. Sound pretty cool, right? All right. Thanks for your time. Take care.